Solution to Renaissance puzzle number 210, area of the triangle. Here is the problem statement. Triangle ABC has a base length of 10 inches and a right angle at apex C. A perpendicular line from the base to the apex has a length of 6 inches. What is the area of the triangle? This puzzle was posed to me by Derek Lane Smith, and he told me that it had been used as an interview question for Microsoft job candidates. At first I thought the problem was trivial. The area of a triangle is 1/2 the base times the height. So 1/2 times 10 inches times 6 inches equals 30 square inches. Simple, right? But no, that is not the correct answer, said Derek. So I thought about it for a while. And eventually it occurred to me that maybe these dimensions can't be right. So here is an interesting fact that will help you see the problem immediately. Look at the circle below with diameter AB. Place a point C anywhere on the upper semicircle and draw lines from C to A and C to B. The angle formed at the apex C will be a right angle. And here's a special bonus offer. Show a proof of this and win a bonus Renaissance point. So if every point on the semicircle forms a right triangle with hypotenuse AB, that means that all right triangles with hypotenuse AB have an apex that lies on this semicircle. And the maximum height of the apex is the radius of the circle equal to 1/2 AB. Since our problem statement said that AB is equal to 10 inches, then the maximum height is 1/2 times 10 inches equals 5 inches. But the problem statement said that the height was 6 inches. Therefore, the triangle cannot exist. Or can it? Let's look deeper. Some of our smarter Renaissanceteers knew about the semicircle of right triangle apex locations and were able to see the flaw in the problem by inspection. Alas, I was not so clever and had to figure it out some other way. Perhaps finding the other dimensions might help. Let's label the unknown sides E, F, and X. We see that the length AD is equal to 10 minus X. And now let's break the figure into 3 separate right triangles. Now we can write the Pythagorean identity for each of these triangles. E squared is equal to 10 minus X squared plus 6 squared. F squared is equal to X squared plus 6 squared. And 10 squared is equal to E squared plus F squared. Next, we can substitute our expression for E squared here and our expression for F squared here. This gives us a new equation with the variable X alone. Now let's simplify this expression. Now expand the square terms. Then gather terms, divide by 2, reorganize, and we have x squared minus 10x plus 36 equals 0. This is of the form ax squared plus bx plus c equals 0. So we can use the quadratic formula to solve for x. And we get x is equal to 10 plus or minus the square root of 10 squared minus 4 times 36, all divided by 2, which simplifies. And finally, we have x is equal to 5 plus or minus j times the square root of 11, which is a complex value. There's the rub. We can't have a side with a complex length. Or can we? Electrical engineers have been dealing with complex lengths in signal analysis calculations for a very long time. We like to plot the complex part on an axis orthogonal to the real part. So let's draw our original triangle of base 10 and height 6 on the real plane. And now let's show the coordinates of the corners of the complex triangle and draw the triangle in. If you do the math, you will find that this is a right triangle at the apex. And if you calculate the area of this complex triangle, you find that the plus and minus imaginary parts cancel out, leaving a real 30 square inches of area. So if you are ever given this devious problem in a job interview, show this solution to the problem poser and say, "Ha! You thought you would fool me by giving me a problem to solve with conditions that cannot exist. But you only fooled yourself, because these conditions can exist and you just couldn't see them. So in your face, Mr. Hiring Manager." Or on second thought, if you really want the job, maybe you should just talk about the right triangles in the semicircle and leave it at that.